what we're talking about is how matter is composed of, and compounds are composed of atoms. You have some compounds that have the same atoms that make it up, but they're different compounds. And so multiple proportions explains that by saying that no matter if you have a fixed mass of one of your atoms, when you compare the second atom in that compound to the second atom in a similar compound made up of the same atoms, then those masses should give you a small whole number ratio. So we talked about carbon dioxide and carbon monoxide. Let's jump in and do one more example, and then we're gonna I'll try to slide in two examples. I think because I think might be able to fit them both in and still get to the next topic. But let's do that. So there's another strategy here. The first strategy we had carbon and oxygen. We found the mass ratios and we simply compared the oxygens, right? So we had those mass ratios. Sometimes you'll see a problem where you actually have the actual mass ratios and you already have one of your atoms resolved to a fixed mass, right? So let's do this problem here. So let's take the mass of oxygen that combines with nitrogen. And this is 1 gram. So remember the last problem, when we're doing multiple proportions, you always want to resolve one of your atoms in that compound to a gram, a fixed mass. So we got nitrogen as the fixed mass, and the masses of, let me fix that right quick. Are 1.142 grams, 2.28 grams, and 2.855 grams. So these are our oxygen masses. So what this problem has already given us are the numbers that we're going to compare, right? So you can attack these problems different ways. They can be presented in different ways. And so the question asks, show how these data illustrate the law of multiple proportions. Just going to abbreviate that as LMP, law of multiple. So what should the data tell us? What should these numbers tell us? If I combine or if I compare the ratios of the masses of oxygen, what does the law of multiple proportions tell us should happen? Anybody? When I compare those masses of oxygen to each other, anytime I make a ratio out of any two of those numbers, that ratio should be a small whole number ratio. That's what the law of multiple proportions tells us. So let's look at it. So let's say compound 1 is 1 gram of nitrogen. It already gave us that. And then we set that equal to 1.142 grams of oxygen. For compound 2, made up of the same two atoms, nitrogen and oxygen. Compound 2, 1 gram nitrogen equals sorry about that. My email is blowing up because I just got onto my 9 o'clock class. Turning in BS and thinking it's acceptable. These are juniors and seniors. You should be on top of your game. Not the game shouldn't be on top of you. And then here, compound 3 is the ratio of the masses of nitrogen to oxygen is 1 gram of nitrogen, and then 2.855 grams of oxygen. So now the way that we show that this follows the law of multiple proportions, we take the ratios of the oxygen, because the fixed mass, it stays. So everything else, the other atom, we're going to compare those ratios to see if we get small whole number ratios by comparing them. So let's do that. Right, so for these oxygen masses, let's take compound 2 and compound 1 and compare them. So in compound 2, the mass of oxygen is 2.28, and then compound 1, it is 1.142. All right, somebody help me out with that calculation. What do you get? Anybody?
1.996.
Good. So 1.996 over 1. We can round that up. So that's going to be a 2-to-1 ratio. So this is a small whole number ratio. And that's the idea. If you compare the masses of the second atom in that compound, they should relate to one another in small whole number ratios. That's what the law of multiple proportions tells us. So we got compound 2 and compound 1. Let's look at take compound 3 and compound 1. Let's compare those. So compound 3 is 2.855. And we're comparing the oxygens now. That's what we're doing. So don't lose sight of that. So 2.855 grams of oxygen, and then compound 1 is 1.142. Somebody give me that number.
$2.5.
Excellent. So 2.5 to 1. Now, here's the thing. So we can't necessarily round that number up because we want it to be a whole number, right? It's got to be a whole number. So what we can do is make it into a whole number. So we're going to take this ratio and make the numerator a whole number. Right? So we're going to multiply top and bottom by 2. And so that's going to be 5 to 2. And again, that is a small whole number ratio. And that's what you're looking for to determine whether or not a compound illustrates the law of multiple proportions, right? And again, this is all based on the fact that you could take 2 atoms and make multiple compounds with them. All right, now let's look at it. And this is again, when I was talking to the class this morning, right? These laws are based on observations. These are not like, we're not pulling things out of thin air. We base them on observations, and then we take the law and apply it to other situations, right? So let's look at compound 3 versus compound 2 and see what we get. Compound 3, compound 2. So compound 2 is compound 3 is 2.855. Compound 2 is 2.28. What do we get from that? Anybody? And again, you want to leave that 1 in the denominator because it is a ratio. You want to display it as a ratio. Anybody got it yet?
(1.252).
Good. So we'll leave that at 1.25 to 1. And again, that's a decimal. And we're going to make the numerator, we're going to make it a whole number. So we multiply top and bottom by 4, right? That's going to give me in the numerator 5 and in the denominator 4. All right, so this is again a small whole number ratio. So this problem asks if we took the data that was given and compared the oxygen data to each other. Anytime we compare two of those numbers, they should resolve into a small whole number ratio. You can see that happened every time. So yes. So the question, let's go back and answer the question. It says, show how these data illustrate the law of multiple proportions. So we did that. And we also know that the data matches up with the law of multiple proportions, because that's what it says. You take the second atom in the compound and you compare them. If there are multiple compounds, you compare that second atom, the mass in each compound, you should get a ratio that's a small whole number ratio. Right? It sounds convoluted, but it's just a way to explain how atoms combine to make compounds. All right, let's do one more. Let's do one more with a different strategy. All right, so we're gonna do another example with a slightly different strategy. We're gonna take an example that says we have 100 grams of 2 different compounds composed of sulfur and oxygen. So this is a key that's just giving us a number, a total amount. Sulfur and oxygen. And the question says the first compound is 50 grams of sulfur. Second compound is 40 grams of sulfur. All right. And the question is asking the same thing. Show how these data illustrate the law of multiple proportions. Just write this down here. So again, I'm just abbreviating that law of multiple proportions as LMP, right? So again, when you attack these multiple proportion problems, one of your 2 atoms has to have a fixed mass. So we want to take one and make it 1 gram. That's the strategy. Right? It's a little bit different than the law of constant proportions, where you just took the ratio of the atomic masses and used that as a conversion factor. That's where this differs from that, right? So in that first example, or in the first sample, we said we had 50 grams of sulfur. How many grams of oxygen do we have if the total mass of the sample is 100 grams? If the total mass is 100 grams, what is the what's the mass of the other part of that?
50 grams.
50 grams. Good. So 50 grams of oxygen. And then the second compound, well, first let's resolve this. So let's divide both sides by 50. So 1 gram of sulfur is equal to 1 gram of oxygen for the first compound. Second compound is, it said, so we're gonna call this C1, C2, compound 2 was 40 grams of sulfur. How many grams of oxygen if the total sample is 100?
60.
60 grams. Good, excellent. All right, so now we're going to take this and resolve. And since the 40 is a smaller number, we're going to divide both sides by 40 and see what we get. So this is 1 gram of sulfur is what? Help me out. 60 divided by 40.
1.5.
Right, of oxygen, 1.5. I don't know if you've picked up on it yet or not, but it's a good idea to have your calculator handy during class. Even though we're not taking an exam or a quiz, you always want to have your calculator handy because I'm always going to be asking people to calculate certain things. So yeah, so now we've reduced sulfur to 1 gram. And what we're going to do now is compare the masses of the oxygen. So here's 1 gram of oxygen. Here's 1.5 grams of oxygen. All right, so we're going to say that, and we want to know if we do that comparison, if it resolves to a small whole number ratio. So let's do that. So compare the oxygen masses. So that's going to be, we'll put the bigger number on top, 1.5. It doesn't matter, but over 1.0 gram of oxygen. All right. What can we do to that top number to get rid of that decimal?
Round to 2.
Okay, we don't want to round it because then the bottom number doesn't change, right? That's really important. That ratio has to stay as is. The only reason we did this, we rounded to 2 here, was because the bottom number was already 1, right? But if we were to round the second one up to 3, that ratio would be totally off. All right. So when if we have a situation like that where the top number is a decimal, but we know that the top and the bottom numbers both have to be accounted for, we're going to turn this into a whole number, right? So we're just going to take both top and bottom and multiply by 2, right? Because we have to take the bottom number and the top number into account. All right. And so, and that other number was so close to 2 that we could just say, okay, this is 2, but this we're actually rounding up by 0.5. So we don't want to do that without touching that bottom number. All right. So then this is 3 to 2. And again, this is a small whole number ratio. Does that make sense?
Yes.
All right. So yes. So this follows the law of, let me fix that P. This follows the law of multiple proportions, or illustrates it. All right. So we've talked so far about the law of multiple proportions, law of constant proportions. We've talked about early atomic theory. We've talked about how to do these conversions and convert masses and determine whether or not a compound meets the law of constant proportion, whether or not a compound meets the law of multiple proportions. We talked about Dalton's atomic theory. So now we're going to switch gears and we're going to move into a different topic, which is to talk about some of the discoveries that helped to evolve atomic theory, right? So because atomic theory at the time, a lot of the pieces to that theory, because you know there are 5 parts to that theory. A lot of the parts to that theory were still being worked out, right? And so that's why that two of the things that came out of that theory were the law of constant proportion and multiple proportions. But now we're going to talk about the evolution of atomic theory. And what I mean by that is there were some breakthrough studies that were done that helped us to discover the different particles that make up an atom. An atom can't be reduced to any other, like a smaller atom. The atom is the smallest part of any element, but the atom does have, as we talked about before a couple of weeks ago, it does have subatomic particles. So it's composed of something, but it's not divisible. I can't chop an atom in half and get a different atom. All right. So let's talk about that. So this is a different, this is going to be a different section, different topic. So under this evolution, we're going to talk about breakthrough studies. Right, for the electron and the proton and the neutron. Right, and then we're going to talk about the different subatomic particles. Right, those two are really combined. And then we're going to talk about isotopes. Right, because the study of isotopes led to the discovery of neutrons. So now let's talk about some of these breakthrough studies. And I want to start out talking about the discovery of the electron. All right, so when we talk about the atom itself, right, this is our model. And I'm going to talk about some other models that were proposed, but this is our model where you have a nucleus made up of protons that have a positive charge, neutrons that have a 0 charge, and then electrons that are orbiting the nucleus that have a negative charge. All right. So each one of these particles, this was not known, right? This had to be discovered. That people had thoughts and hypotheses about how the atom is composed, but in reality, the discovery of each one of these particles was a separate discovery. And so the first discovery, or the first part of the discussion, is dealing with the electrons. And this was done by J.J. Thomson. And I have there's a, when I open up the next quiz, it's going to be based on Thomson's, his experiments to find like the electron and find out like find this subatomic particle. He didn't really know it was an electron. That name came later, but he called it something else. But he knew that something was being ejected from this atom that was a part of the atom, but it had a negative charge, right? So what he found out, and I'm just going to distill this down to the most pertinent information. like what he found out was electrons were very light. So they had a mass about of about a 1/1000th of an atom. Right? Very important. Super, super light. And we're going to talk about the mass of an electron later when we talk about some other studies. What he also found out, based on his work with cathode rays, which we later found out were beams of electrons, that atoms were composed of smaller particles, right? That were not atoms, but components of an atom. Right? We have the benefit of hindsight, so we know what the structure of an atom is. We got more advanced equipment, all of that. But again, these were like seminal studies in these areas. And another part of this was that his cathode ray but let me not say that. The particles that made up the cathode ray were negative. They had a negative charge. Excuse me. All right, so they had a negative charge. They had a very small mass, and he knew that these weren't atoms being divided, but that the particle had to be some other part or component of the atom. So let me switch my screen right quick, and I want to show you his experimental setup. So this is his experimental setup. So this is called a cathode tube, and there's an element here, and as he passed high voltage through that element, and it passed from cathode to anode, there was a beam here that was negatively charged. So this cathode ray was actually a stream of electrons being emitted from whatever element or atom was here that was being electrified. And what he noticed was that with the cathode ray, notice how the beam kind of shifts up here. That's because the particles that make that ray up are attracted to this positively charged plate up here, right? So there's some particle that's makes this cathode ray up that's negatively charged, and it's attracted to this positive plate. So that's why you see the bend here. And so what was eventually found out was that those particles were actually electrons being emitted from an element. All right. And so there's another study that kind of tied in with this by Milliken, Robert Milliken. And Robert Milliken just kind of put the icing on the cake as far as like what the charge is. He kind of, verified that the charge of an electron is negative. And he also found out the mass of an electron. So he found out that the charge on an electron was 1.6 times 10 to the minus 19 coulombs. All right. And he also found out that the mass of an electron could be derived from previously known data. So previously, the mass to charge ratio for an electron was given. So it was 1 kilogram per 1.759 times. Let me make sure that this number is correct. Oh, hold up. I need to go back to, I need to go back to my iPad too. Sorry about that. Because you can't see what I'm writing. All right, but let me show you his apparatus first, and then I'll go back to my iPad. So this is his apparatus, and so he's spraying in these oil droplets, and he had 2 charged plates in here, and the charged droplet that comes from the top plate to the bottom plate, he was able to observe through this eyepiece, right? And the X-ray is what was used to produce the charges. But what he found out was that the charge for every different type of droplet, the charge on it was some multiple of 1.6 times 10 to the minus 19 coulombs. And so that's how he was able to determine the charge on one electron by looking at the charge here and noticing that there was a trend. You see it's 1.6, 4.8, 3.2, and 6.4. All right. So let me switch back to my iPad right quick. And then we'll finish talking about this. All right. So he found out that the charge on an electron is 1.6 times 10 to the minus 19. He also, based on this information and previously reported, this is what we call a mass to charge ratio. So based on this information, he could solve for kilograms, right? If he knew that the mass to charge ratio for an electron was 1 kilogram to 1.759 times 10 to the 11 coulombs, he could take that and just multiply it by the 1.6. And the coulombs would cancel and he'd be left with kilograms. So what he found out after taking that data and using it and taking the charge and using the mass to charge ratio as a conversion factor, he found out that the mass of one electron is 9.107 times 10 to the minus 31 kilograms. So that's the mass of one electron. Right. And again, this is all groundbreaking information, all new information. So with that, now we know about the electron and how the electron was eventually discovered and what the charge is on the electron and what the mass of an electron is based on the work of Milliken and based on the work of Thompson and many other scientists who were like working in this area. So with that being said, let's talk about the proton. All right, and before we do that, are there any questions about the electrons, about the numbers, anything dealing with the electron? So again, this is why conversion factors are important and understanding how to manipulate them. Because Milliken taking that mass to charge ratio, if you know the charge and you have that conversion factor, you can convert between the charge and the mass, even though they're 2 separate units measuring 2 different things. That ratio means that you can use it as a conversion factor. Anytime you have a ratio of 2 units or 2 things, you can use them to interconvert between the 2. So let's talk about the proton, and let's talk about Ernest Rutherford. All right, so Rutherford did this gold foil experiment, right? And without all the gory details of it, because I'm gonna show you the experiment in a second, like what he was able to do. Well, what he found out was this, that there is a particle in the nucleus of an atom that's really heavy and positively charged particle. Right, so that's one of the findings of his study, that there's a heavy, we know now it's a proton, but back then they didn't know that. So a heavy positively charged particle in the nucleus of all atoms. What he also found out was that electrons right? They occupy the most space within an atom. So the nucleus is very small compared to the space that the electrons occupy. Even though the electrons are very small, we're going to talk about later how those electrons are mobile. Like they don't sit still. They're always moving and orbiting that nucleus. All right. So the electrons occupy more space than the nucleus, but most of the mass is concentrated in the nucleus. All right. So most of the mass of an atom is concentrated in the nucleus, and that heavy positively charged proton is about 8,000 times heavier than an electron. So I'm going to abbreviate electron as E minus. Anytime you see that, that's an abbreviation for electron. All right. So let me show you his experiment, right, with this gold foil. I think it's really, really, really cool. So let me show you that right quick. So this is, let me slow this down too. This is his experiment. So we're gonna slow this down to nothing. So what he did in this experiment was he passed alpha particles through a lead screen with at a certain aperture, like an opening. And the idea is if the atom was only made of electrons and nothing else, because again, at the time they didn't know this, and those electrons are so light that when you pass something, a positively charged particle through, right, there should be nothing should happen. It should just pass through. But what was found out was that as they passed particles through, that some of the particles would get deflected. Do you see the particles that are bouncing, kind of bouncing off like a pinball? Right? Some of those particles would get deflected. And where they got deflected to, they were able to determine, because this screen, this zinc sulfide screen right here, would change colors with those particles. It would be like light green. So of course you'll see a concentration of color right here, because there weren't like that many particles being deflected, but the particles that got deflected to other places, and even the ones that got kicked back, because you'll see some of them going backwards, they were able to also be picked up, right? And so what Rutherford kind of determined based on this gold foil experiment is that only the alpha particles that struck the nucleus of the atom got deflected. Because if you notice, you see all these moving parts around the nucleus, these are the electrons around the nucleus, right? And so only the particles that struck the nucleus got deflected. So that must have meant that there was a really heavy particle in the nucleus that was heavy enough to cause that deflection. And so that's how, and that the particle was positively charged, right? The positively charged part, these alpha particles are positive. And anytime charges come into contact, what's the rule? What did you learn in like high school chemistry or high school physics about charges? Do like charges attract each other or do they repel each other?
Repel.
They repel each
They
other.
re-
So that's
They
why
repel each other.
yes, exactly. So when you see those particles getting deflected, that also gave a hint as to the nature of that nucleus, that it had to have a positive charge. Because if you hit it with a positively charged particle and that particle gets deflected, that means that the nucleus also has to be positive, right? Because if you notice as those particles pass by the electrons, the moving parts, nothing happens. But when they hit that nucleus, they get deflected. And so all of this information led to Rutherford being able to determine that the nucleus of the atom is fully positive, that there has to be some heavy particle in the nucleus that was able to deflect these alpha particles, and that heavy particle we later termed to be a proton, right? It's a proton. So we found out about the protons and electrons, and then as far as neutrons are concerned, right, they got discovered a different way. And then we're gonna save that until Friday. We'll talk about that on Friday, about the isotopes. And then we're gonna move on to another section on Friday as well. All right, any questions about anything? I thought this was a real cool depiction of this experiment. And I told the class this morning when I started looking at these streams of particles, like these alpha particles and X-rays and cathode rays, I immediately thought of Ghostbusters and those their proton packs that they use to trap ghosts or whatever. I'm sure that idea came from somewhere here in one of these experiments, either the cathode ray or this alpha particle ray, one of the two. But yeah, if there are no questions, I'm gonna stop sharing. I'll post the notes in the video. Thank God I didn't forget to record.